Now let's look at the second type of application of nuclear fission, and this is the peaceful version, the desirable one, is to how to build a fission nuclear power plant. All the world's nuclear power plants in operation as of today are based on nuclear fission, not fusion. And some countries like Iran, they claim that they are building their nuclear program for peaceful use. But the thing is, this is dubious because from technical point of view, the same fissiles are being used for both nuclear power plants and nuclear bombs. The difference is the amount of enrichment. Okay, in the case of nuclear power plant, you want to produce nuclear energy in a controlled manner. Energy is released gradually in a controlled manner. So the chain reaction that you want would have a K effect of 1. Okay, one neutron initiating the first stage in nuclear reaction produces effectively only one neutron going on to the next stage. The other 1.5 or 2 neutrons are just escape. Okay, so this one neutron goes on to the next stage and then goes to the next stage. Well, if you use K effective generically, then after one stage you can get this many neutrons. After the next stage you get this many squared neutrons and so on. If K effect is greater than 1, it's going to be it's a runoff reaction. But if K equals 1, then you can have a chain reaction which produces energy at an even pace. That's what you want in a nuclear power plant. So again, you want K effect to be equal to 1. That is called sustained chain reaction, not runaway, not diminished. Okay, and we do not want this to turn this into a bomb, even in the case of an accident, and therefore, because of safety concerns, we do not want the enriched uranium in the fuel rod. We want only 2 to 5% enrichment instead of 90% or higher. This ensures that even if there is a catastrophic failure in a power plant, the worst that you can get is a meltdown, not a nuclear explosion. Okay, will it ever explode like an atomic bomb? No, because there is not enough concentration or enrichment of uranium-235 to produce a runaway accident. The problem with nuclear, with accidents in nuclear power plants, we'll see more details in a bit, is that you are unable to control this process so that K effect can be greater than 1, even if you shut it down, so no new power is produced that way. The heat that is generated by nuclear reaction can cause the nuclear core to melt, or even cause an explosion of the roof of the building that contains it, as in the case of Chernobyl. And then as a result, you have a very hot radioactive core, which can produce radioactivity into the air, into the land, or into the ocean, and so on. So it is the nuclear pollution that you're really worried about, not the nuclear explosion like an atomic bomb, because this will not happen due to the far less enrichment compared with the bomb grade fissile material. Okay, so it is the radiation that leaks into the environment that we should really be concerned about. So, how does one control K effective so that it remains equal to 1? And if it's not equal to 1, suppose there is a spike in K, how do you lower it quickly? Well, we have to look at the factors that affect K. Neutron escape and absorption, and neutron capture cross-sectional. These are the things we worry about. We have to consider. How do we consider? Okay. Some neutrons will escape. That's inevitable. So we have to find a way, because we're looking at far less enrichment. There are not a whole lot of fissile materials to concentrate it. So in order to sustain that chain reaction, to make sure K is not less than 1, we have to make the neutrons that are generated from the nuclear fission more efficient. That is, they are more likely to be captured by the next stage nuclide to produce another step in the chain reaction. So I want them to be more visible to the other nuclides. That is to increase what's called neutron capture cross-section. So here's the thing. If a neutron comes in at very high speed, which is the case when a neutron is just produced by the previous stage. We're talking about several MeV of kinetic energy. Okay, they move so fast, and here's a problem: when they move at that kind of speed, we're talking about, 10,000 kilometers per second. With that kind of speed, the problem is, first of all, they are more likely to cause an elastic collision with other with the fissile nuclide. Elastic, which means they just go off like this, without being actually captured. Okay, that's one thing. Another thing is that they spend so little time being close to the target nuclide, that there is very little time for this nuclide to actually grab it. So therefore, fast neutrons with a kinetic energy of a few MeV are not very desirable in terms of producing the next stage nuclear reaction. In general, the slower the neutrons move, the more likely they will be captured by a fissile nuclide to produce another stage of fission. So therefore, we want to reduce the speed, reduce the kinetic energy from a few MeV to a fraction of EV, which make them what's called thermal neutrons. Thermal neutrons are neutrons in thermal equilibrium with their surrounding. In a nuclear reactor, we're talking about, of course, higher than room temperature. If it's at room temperature, K is only 1/40th in EV. Okay, but even in a nuclear reactor, the temperature is not incredibly high. So therefore, thermal neutrons move a lot slower because their kinetic energy is only a fraction of EV instead of several million EV. We have to turn these neutrons into thermal neutrons by dramatically slowing them down. Therefore, they are more easily captured by next target. Okay, so how do we do that? We have to use something to slow them down. These materials are called moderators. So fast neutrons produced by fission, after going through a moderator, they are slowed down dramatically, giving up most of their kinetic energy, become what's called thermal neutrons. Okay, so how does this neutron lose kinetic energy? If you look at collision, you look at our discussion of collision in physics 1A, you find that the most efficient way for a particle to lose kinetic energy is by colliding with another particle of identical mass, right? Elastic collision between two identical objects with the exact same mass, like two billiard balls colliding with each other. What happens? The first one stops. Okay, the first one first comes in and hits this stationary one, and the first one stops. The second one carries all of this kinetic energy and moves on forward. So there's 100% transfer of kinetic energy. On the other hand, if this neutron collides with something much more massive, okay, just like a ping pong ball colliding with a wall, after that, the ping pong ball reverses its direction with the same velocity, of the same speed, I should say. And therefore, there is zero transfer of kinetic energy. So 100% transfer for the same mass, 0% transfer for totally different masses. Of course, in reality, we're looking at somewhere in between, 100% and 0%. But the idea is the moderator should consist of particles of roughly the same mass as the neutrons in order to absorb most of the kinetic energy from these neutrons. So who has roughly the same mass? What about a proton? Right? What about proton? And therefore, we should look for materials with a lot of protons in it, and protons do not exist by themselves. They exist in charged neutral atoms, such as hydrogen. Okay, so we should use materials that are hydrogen rich. How about water? Therefore, water is a candidate for a moderator. Again, the moderator serves to slow down the neutrons, turning them into much slower thermal neutrons, making them more effective to trigger the next stage of fission. So moderator is what makes K up. Okay, K effective up. On the other hand, if K effective is too high, you got too many neutrons, you run the risk of meltdown. The temperature would go up uncontrollably, and then what do? You want to take away some of these neutrons. And that actually is pretty easy to do in a nuclear power plant setting. All you do is you insert into the moderator where the neutrons are moving, you insert materials that can easily absorb these neutrons. Cadmium is a material for that. So a lot of these neutrons get absorbed, so therefore the K value goes down, and the reaction rate goes down, temperature also goes down. Okay, so these are the two primary things we do to control K effective make sure it doesn't go too high, doesn't go too low. One is moderator, which tends to increase K effective, and absorber, or in a physical form of control rods. Okay, we make these control rods out of things like cadmium to absorb the neutrons in case the K effective gets too high. So in a power plant, the temperature of the reactor core is monitored carefully. The temperature is supposed to be even. Okay, that is when you have a normal running environment. If the temperature tends to be too high, that means K has shot above 1, and then what you do is you lower the control rods into the moderator. The control rods will absorb some of these neutrons. That will decrease the reaction rate, and K will go down. So the control rods are controlled automatically by the computer, which monitors the temperature, and that's how we maintain K effective. Here is a flow diagram from the textbook. This is a type of nuclear power plants called pressurized water type. Most of the nuclear power plants in this country, the United States, are of this type. So we have two loops, so-called primary loop and secondary loop. Here's what's going on in the primary loop. This is the core of the reactor. You have uranium fuel rods enriched to between 2 and 5%. Okay, uranium fuel rods, and you have the control rods. And in between the uranium fuel rods are the moderator, which is water, liquid water. It is, in fact, the temperature is considerably above 100 degrees. So you have to pressurize it so that the water, even though at such a high temperature, remains liquid. So that's why they're called pressurized water type. Now, this water acts as for two purposes. One is they are moderators, so slow down the neutrons coming out of the nuclear reaction, and they also act as heat transfer media. So they take the heat away from the reaction, nuclear reaction, and then in this loop, you have super high temperature water here, and that they exchange their energy to the water outside to produce steam, and that steam is being used to run the electrical turbines that produces electricity. Okay, so that's in the secondary loop. So that's how the typical pressurized water nuclear power plant works. This pressurized loop must be extremely tough and strong, and they have to build a large size, and that takes a lot of technology. Not all countries have the large heavy industry machinery to produce a strong enough hard casing which can sustain such an incredible amount of high pressure. Okay, so that is one type. There is another interesting type the textbook did not discuss. It's called a breeder reactor. Those reactors are magical in the sense that as they produce electricity, they also produce the fuel for another reactor, and they would actually produce more fuel than the ones they consume. These are breeder reactors. Breeder means they're breeding energy. Breeding the fuel for another reactor. They produce more fission fuel than they consume. And as a result of that, if we mine the uranium from the Earth's ocean and use them exclusively in breeder reactors, then in theory, we have enough uranium in the Earth's ocean to produce energy for the next 5 billion years. Another advantage is that they produce less nuclear waste, radioactive nuclear waste. So how do breeder reactors work? What's the mechanism? Well, the mechanism is very simple. Okay, the most abundant uranium form in nature is Ch45, and unfortunately it's not a fissile, right? Because what is wrong with Ch45? What is wrong is because unless you give it a fast enough neutron, it's not going to produce enough energy to split apart. So therefore, it just absorbs a slow neutron. That's it. It goes into Ch39 and it just stays there. It does not undergo fission. Therefore, it's useless. So you say, all right, why don't I give it a fast neutron? Okay, if I give it a fast neutron, it will have enough energy to split, right? So here's what's going on: a fast neutron hitting a Ch38. Ch39 with enough internal energy, then splits apart into this new element, which undergoes beta decay, and eventually you get plutonium-239. This is an excellent fissile. So you can turn the useless 238 to useful plutonium-239. This process happens in several steps. The first step, the half-life from is only 23.5 minutes, and it's going to take about 2.5 days to get neptunium. But the last step, the most critical step, where you produce actually useful fissile fuel, that takes long. That takes 2.4 times 10 to the 4 years. But still, that's half-life. Okay, that's half-life. So you don't have to have entire thing turning into fissile. You can wait a little bit. You know, we're talking about a few years. You will get enough plutonium accumulated. So the question is, who gives you this fast neutron? The fast neutron is produced by plutonium-239, the end product. So we have to start with a core of plutonium-239. Okay, so we have a core. This core is surrounded by a layer of uranium-238, the otherwise useless material. Plutonium produces enough fast neutrons by decaying. In fact, this plutonium we have to enrich it to about 25 to 30%. Okay. And as a result, it's going to produce enough fast neutrons, and these neutrons will be absorbed by 238, which slowly turns them into plutonium-239. So you start with a certain amount of fissile, and then as these fissile turn into undergo fission, they produce energy, and they produce over time more fissile. That is how the breeder reactor works. And a key technical factor for this is what is the plutonium breeding ratio, and that is for every plutonium-239 that you supply, how many do you get out of it as a result of this breeding process? It has to be greater than 1. That's how you consume less and get more. Okay. Now, ideally, we're looking for something greater than 1. In reality, it's about 1.01 to about 1.2. But still, that means we're actually getting more fissile out of it than the one we produce. And another thing is doubling time, and that is, if you have, say, a gram of plutonium-239 to begin with, how long do you have to wait to get 2 grams out? You double the fuel supply. And it turns out the time is about 10 years. 10 years, and it's primarily due to the last stage. Okay, now the breeder reactor, the United States built these reactors in the 1950s, primarily because the process of enriching 235 for a conventional reactor was very expensive. Okay, in this case, you don't need 235, you just need 238. But gradually, as the cost of enriching 235 came down, because the U.S. found a better technology of doing that more efficiently, they found that the overall cost of running a breeder reactor is higher than a conventional reactor, so therefore it became less of an interest to the U.S. But another advantage of the breeder reactor is that, again, it produces less pollution, so it may become more prevalent in the near future because of that reason. Now, in a breeder reactor, we do not use water, pressurized water, to take away the heat. Rather, we use liquid metal. Okay, so the primary type of breeder reactor is called LMFBR, liquid metal fast breeder reactor. Liquid metal because the metal is at very, very high temperature, so they're liquid. We use mostly sodium. Why use sodium, not water, as a moderator? Okay, it's because water is a moderator. It's not just a heat transfer medium, it's a moderator. And normally a moderator is desirable because we want to slow down these neutrons, right? In a typical conventional reactor, we want to slow down these neutrons so that they become more useful to go on to the next stage. But here, we're looking at 238. If you give it a slow-moving neutron, it's totally useless because it will not fission afterwards, after absorbing the slow neutron. You need fast-moving neutrons. You do not want to slow down the neutrons that are produced by plutonium. And as a result, You do not want the moderator effect. Okay, so we do not use water for that reason. We use liquid metal. Liquid metal. Sodium is the primary material we use, but that raises safety concern because sodium is a highly chemically reactive metal, so you do not want to expose to the air and so on. So there are safety concerns to deal with. Okay. Another common type of nuclear reactors is the one designed by Canada. It's called CANDU reactors. It's unique because they use heavy water instead of light water. CANDU stands for Canadian Deuterium Uranium. Deuterium, as you know, is a heavy is an isotope of hydrogen. It's got two nucleons, including one proton and one neutron, and of course one proton. Okay, so that is a rare isotope of hydrogen. So they use heavy water D2O instead of regular water H2O as a moderator. What is the advantage of D2O over H2O as a moderator? Well, the thing about D2O is that D already has a neutron. If you use H is excellent as a moderator in slowing down the neutrons because they have almost the same mass as the neutron. But the problem is sometimes the proton want to combine with that neutron, so it does not always just slow it down. It sometimes just recombine with it. The recombination just kills that neutron, right? Just take that neutron out of commission. And with D instead of H, it already has a neutron, so it is far less likely to absorb one more neutron. And as a result, it is a more efficient moderator. When you have more efficient moderator, you do not need such high amount of enrichment as to sustain chain reaction. And because they use D2O instead of H2O as a more efficient moderator, the Canadian nuclear reactors do not need an enrichment of 2 to 5% uranium-235. They only need about 0.9 to 1.2% enrichment. In fact, these original CANDU reactors designed to run on 0.7% 235, which is totally natural uranium. And there was a reason why the Canadians did that, because right after the war, they wanted to build power plants, but they found that enriching uranium was just too expensive to do. So they had to find ways not to enrich uranium, and that's the solution that they came up with. And the CANDU design is the primary design of Canadian reactors. They have over 17 reactors running on that principle, and some other countries, including China and India, have imported this technology as well. But the CANDU reactor does have its shortcomings as well, primarily because the cost of getting heavy water, it's about $1.5 billion worth of heavy water each plant. So that's a concern that we also must address. Lastly, let's look at the nuclear power plant that's closest to us, Los Angeles. That's the San Onofre's nuclear power plant. It's about 80 miles away from Los Angeles, midway between San Diego and Los Angeles, right on the coast of the Pacific Ocean, close to I-5, interstate highway. It has 2 active reactors running today, producing a total of 2,200 megawatts of energy. That is 1.4 million households worth of electricity usage. It is of the conventional pressurized water type. Okay, is it safe? Well, authority says it is. But there are some incidences. The one as recent as February the 1st, 2012. There was a radioactive gas leak from a steam generator. But authorities say that the leak of radioactivity into the atmosphere is negligibly small. It will pose no danger to public safety. And what about earthquake threats? What if there is an earthquake or even a tsunami that comes with it? What's going to happen? Well, the San Onofre's nuclear power plant is designed to withstand an earthquake of 7.0 magnitude directly under the plant. What if there's an earthquake bigger than that? Well, the worst thing that can happen is like the Fukushima incident, which we'll talk a little bit later. And that is when due to the malfunction of the cooling system, the core melts down. When the core melts down, radioactivity can leak into the air, into the ocean, into the ground, and so on. The chance of such a core meltdown event due to a very large-scale earthquake every year, the risk is 1 in 58,824, according to a government estimation. It sounds like a small chance, but the risk is there. So basically, according to our textbook, there are 3 layers of defense against a breach of a nuclear power plant. One is there's a core. The core is made of very strong materials, but the core can melt or can rupture under extraordinary circumstances, and then the radioactive material then leak into the next layer, which is the concrete encasement of the building. In the case of Seminoferous, look at these spheres. You probably have noticed when you drive by. The thinnest part of each sphere is 1.8 meters or 6 feet. Now, what if even this layer is breached? Then, unfortunately, it's going to go into the environment. So the 3rd layer of defense is hopefully they build something like this in a remote area, not very far, not very close to densely populated regions. But in the case of Seminoferous, that is not quite true, because it's they're building towns right next to it, and they're not that far from Los Angeles or San Diego. So this is always a concern. We have to weigh the benefit against the possible hazard. It's always the case with any technology. Later on, we're going to take a look at accidents, famous accidents in nuclear power plants, how, if anything can be done to prevent them, and what if there's a radiation leak, what kind of damage can it cause in living organisms such as the human body. And we can also look at the alternative to nuclear fission, and that is nuclear fusion. It is a much cleaner source of energy, more abundant and cleaner, but why are we not using it to produce electricity today? It's because of technical difficulties. From a physics point of view, we'll address those issues as well.